A very good morning to all of you, and today we'll be proceeding our series of lectures, and we will start with an extension that we have discussed in the previous video. We tried to go on with time-dependent perturbation theory, and obviously we came up across some of the calculations and some of the results that we have obtained. And I think that the last result that we obtained for time-dependent perturbation theory was first order correction, and then we evaluated the expression for transition probability, what is probably known as Fermi golden rule. Now let's go on extending our understanding of this time-dependent perturbation, and there are two important domains in which we can make calculations to predict an action. That action can translate our system from one quantum state to another quantum state. So to speak, we'll be talking about these two important approximations as an extension to that basic mathematical model that we have achieved till now. This model will automatically lead us to the two important approximations in advanced quantum mechanics, as adiabatic approximation and the certain approximation. Now, as talked about earlier, approximations are important in physics. You don't have anything exact in physics. We always rely on these approximations, and what these approximations does, they help us simplify the complex problems. We can solve the complicated problems using appropriate approximations, and we can boil down the results that are consistent, the results that can be relied on by actually simplifying the complex problems into the simpler ones. And they are very useful techniques when exact solutions are not possible, as I said. And we have two common types of approximations that we can see in advanced quantum mechanics. One is adiabatic approximation, and the next one is the certain approximation. Now, talking about the first one, which is adiabatic approximation, let me give a small concept to understand this approximation. It certainly applies when you have changes in the system, and these changes, they do occur slowly. So there is always a state of relaxation for the system that evolves from point 1 to point 2. And the system has time to adjust, because when we say there is an adiabatic change, when we treat things adiabatically, the system has enough time to adjust to the new conditions. And as an example, we can think of a glass filled with water, and if we tilt it slowly, the water will readjust in the new orientation that the tilting results in. So we can say that when we talk about the adiabatic approximation, the perturbation that you introduce, that perturbation causes that perturbation is slowly varying. That is slowly varying. Okay, so when we use it, when the external environment that you are providing to your system, when it changes gradually, when it changes slowly. So in slowly varying magnetic field or electric field, we can think of adiabatic approximations, because here we are treating our external perturbation that we are inculcating on our system. We assume that this change is extremely slow in nature, and this is what makes it important in many quantum and atomic processes. So, this is an idea about the adiabatic approximation. As we move on, there's another approximation, what we call as sudden approximation, and the name itself reflects the action of the system. Sudden. So what happens here applies when changes are very fast. They're abrupt. That there is no chance for the system to adjust the way it was in adiabatic approximation. The system was evolving very slowly, allowing the system to readjust itself. But when we talk about the sudden approximation, we have an instantaneous change. The perturbation that we are introducing into the system leads to the instantaneous change. So the system does not have time to adjust. So in adiabatic approximation, the system has enough time to adjust or reset itself. But here in certain approximation, we don't have any time. And we can think of yanking a chair from under sun. So if we yank a chair, somebody is sitting on a chair, we will yank the chair. This will give a sudden drop to the person sitting on the chair. That can be treated as sudden approximation. Can get an idea about this approximation. So when we use it when the external fields, external perturbations that you are inculcating on your system, they are rapidly changing. So what's its implications? The implications are we can model the quick interactions that are taking place between the particles in the quantum systems. If there is an interaction between the two particles, so these interactions we can understand those interactions to some extent using this sudden approximation, and it's often used in nuclear and particle physics. Now, if we compare the two approximations, as we said, adiabatic, slow change. System follows the change. The system is subjected to the change, but that change is very slow. For the sudden, there is fast change, and system remains as it is momentarily. So we have these are the two different tools for different physical situations. So you can have a situation where adiabatic approximation will be useful, and you can have a situation where certain approximation will be useful. Now, the point is that why these approximations matter, because they provide us an insight in the quantum behavior of these systems. They certainly do simplify our calculations. If we don't have the approximation tools, then it's practically impossible to make the exact calculations of these problems. So you yield the result by using these approximations without the major loss of the accuracy. And these approximations, they are foundational in physics, they're foundational in physics and chemistry research. So to summarize, adiabatic, it's a slow change. System has enough time to adjust itself. For certain, there is fast change. System cannot adjust in time. And both of these approximations, they help us understand the time-dependent quantum phenomenon. Now let's move on with our mathematical formalism for both of these approximations. Okay, so let me get it out. So just make it something like this. Now let us first write down my probability, and if I choose P and M, and this Pn is calculated in the previous video, and this is 1 by IH bar. Then you have integral 0 to t. Then we have the expectation psi m h. For h, I will directly use the perturbation in terms of the potential that's dependent on time, and then I will have psi n, and then I'll have e to the power of iota omega mn t dash dt dash, this whole square. This whole square will give us the probability, and this is exactly that we have achieved in our previous video. Maybe the symbol that we have used there, there might have a little bit of variation. Here I'm using P because I want to put down things in terms of the probability. I believe in my previous video I chose it as omega. Now let's move from here, and then let's try to understand these two important phenomena in quantum mechanics. One is adiabatic approximation, and another one is the certain approximation. Now let me see. See, we have an integral inside. If I integrate these two things, what I have 1 by IH bar. So what we will have, u as x, so psi n v of t psi n, and integration of v. So integral of this exponential function, so get here. So what will be the integration of this? It will be the exponential function as e to the power of I omega mn t divided by I omega mn. Okay, this will be the first term. Then we will have minus integral of 0 to t, and the differentiation of the first term, that is this expectation value. So I will be writing d by dt of psi m v of t psi n. Okay, differentiation of the first and the integration of the second. So the integration of second will give me the same result, the result that I've obtained here. Let me go here. So what I will have P and N is will be 1 by IH bar, and then times psi n v psi n v of t psi n, and e to the power of I omega mn t divided by I omega For this, we have the limit from 0 to t. Then we will have minus, I will take this I h bar to the next term also, so this will be times 1 by I h bar, and then we will have integral 0 to t, okay, the differentiation of this term, that is d by dt of psi m v of t and psi n, and integral of this term, the integral of this term will be e to the power of I omega mn t dash divided by I omega mn. Okay, this whole thing has a square. This whole thing has a square because this is the probability density. This is the probability of having a transition or not having a transition. So what we have here is, we can see that if we see this term, what we do is we define our problem. The problem is definable between 0 to t. So if we look at this term, this whole term will be 0. This whole term will be 0 at the limit of 0, using the limit 0 and t. So we will have a complete rid of this term. So what we will be left with is, we'll be left with this term. But keep one thing in mind, we have the square of this. So this whole thing is 0. When we apply the boundary conditions for the perturbation that we introduced to the system, for a span of time from 0 to t, and this thing will not exist for the boundary conditions that we have given as 0 and t. So what we'll be left with is, we'll be left with this thing. So let me write down this thing now. So P M N. Okay, so you have a mod, then I have 1 by I h bar. Okay, then we will have integral 0 to t, then we have d by dt of psi n v of t psi n, and e to the power of I omega mn t dash dt dash. Okay, this whole thing we have got divided by I omega. And we have the square of this whole thing. And we have the square of this whole thing. So we can immediately see that this iota and iota will multiply. It will give us minus, and that minus will become plus. So what we will have here is 1 by h cross omega. So we have to take square of 1 by h cross omega. So we can write down outside as 1 by h cross omega. And inside we'll be left with integral 0 to t d by dt of psi n v of t psi n. Okay, and then you will have e to the power of I omega mn t dash and dt dash. So this will be my starting equation, which I will use to discuss the results of the adiabatic approximation and the certain approximation. The first approximation that we have is the adiabatic. So for adiabatic, what's the necessary condition? The condition is that the perturbation that you are introducing to the system, this perturbation slowly changes. So if this perturbation slowly changes, then we will say that this term in whole will act as constant, because v of t is changing slowly, And if you take its variation with respect to the time, this term will be treated as constant. So what will happen for adiabatic approximation? So now I'll be using the adiabatic approximation. So what I'll do in this approximation, my d by dt of psi m v of t and psi n will be treated as constant. Now, if it will be treated as constant, it immediately means that this variation that we have, it will lead to zero. It will lead to zero. So let me get it out of the integral. So P and n. This P and n gives me the transition probability, and P and n will be 1 by h cross square omega square d by dt of psi m v of t psi n. Okay, this thing is in the parenthesis. It's the square of this, and then you have the integral 0 to t e to the power of I omega m n t dash dt dash. And this also has its own monofold square. So what we are able to do is we have got this expectation value of perturbation outside the integration, and inside we have the exponential function. And as you know, we have solved this integration while discussing time-dependent perturbation. The result of this integration is simply, so if I write down P and n, this is 1 by h cross square omega square, and then d by dt of psi m v of t, then psi n sine square omega m n of t divided by 2. We have already solved this integral in the previous lecture, so the value of this integral will come out to be sine square omega mn of t divided by 2. Now, what is more logical here is that what we have done is we have treated our system adiabatically, and that means the perturbation that we're introducing to the system, it is behaving like a constant. So if it behaves like a constant, it comes out of the integration as x. Now, what we say here, so it has to be the square. It has to be the square. Now, since this term is a constant, we can immediately say that the magnitude of this thing, what we have is d by dt of psi m v of t psi n whole square. This must be very, very less than that of E. What's my final transition is M. What's my initial transition is M. So this is the condition. This is the condition for having this adiabatic condition that we have imposed on this probability. So what does this reflect? This reflects us that the term in the right hand side, that this term will also tend to zero. It will tend to zero if the variation of the perturbation is chosen such that it almost behaves as a constant. So if it behaves as a constant, then this whole term is going to be tending to 0. So if it tends to 0, what we achieve from this? If it tends to 0, we achieve that this P and N, this is the probability of the transition. This probability of the transition will tend to 0. So how can I translate it in a kind of physicality to understand what actually I am achieving by using adiabatic approximation? So if we have a two-level system where we are subjecting the system to an external perturbation, and if we assume that the external perturbation is, it has to be small at the very first point, because only then we will call it a perturbation. The next important thing is I'm assuming that this perturbation is changing very slowly. So if this perturbation is changing slowly, then the probability of the transition, say this is say n and this is say n, then the probability of the transition of your quantum system from the state En to the state Em is 0. So in other words, you are treating your system with an external disturbance, but there is one reality. What is that? The reality is that your system will not undergo any kind of transition. There will be disturbance to the system, but you cannot expect a transition of your system from one quantum state to another quantum state. So this is what will fall in the framework of adiabatic approximation. Now, moving on to the next, what we call as certain approximation. So certain, I have tried to reflect this approximation as certain. You try to change the thing certainly. So what was our starting equation? It was P and M is the mod of 1 by h cross omega square, then you have an integral 0 to t, then you have d by dt of sine psi m v of t psi n, and then you have e to the power of I omega m n t dash dt dash, and this whole mod of scale we have. Now, what we are assuming in certain approximation, we assume that there is that the function is certainly changing. There's a fast changing situation. Now, if your system has been subjected to a change, but that change is so fast, it's so sudden. If it's so sudden, what can we think about this exponential function? This exponential function will not, it will not change because of the sudden action. Because the action is taking place very fast, the action is so fast that you cannot predict the change in your exponential function. You cannot predict the change in your exponential function. So this exponential function can be treated as a constant. And when we will take the mod of this exponential function, what will that give us? E to the power of I omega m n t dash. If I take its mod, that mod will lead me, the scale of its mod, it's like multiplying an eigenfunction with its complex conjugate. So multiplying an eigenfunction with its complex conjugate will give us a number. So this exponential function, if I take the mod of stan of this exponential function, because the perturbation that is introduced here is certain. It's fast. When it is fast, then this exponential function is not going to change. It's not going to change. If it's not going to change, it will be treated it can be treated as a constant, and if you take its mod of square, that will be equal to 1. So in this case, what we'll be left with? We'll be left with Pnn is 1 by h bar square omega square, then you have the mod of integral of 0 to t d by dt of sine n v of t and psi n. This is the mod of whole square. Now what is so important here is that we can directly cancel the derivative with the integral. So this derivative can be cancelled with the integral. So this derivative can be cancelled with the integral. So what we'll come up with? We'll come up with Pnn is 1 by h cross square omega square and the square of psi n v of t and psi n. So the result that we have been obtaining here is a clear indication. It's a clear indication when you subject your system to the certain approximation, then you certainly have a probability of transition. Your system is going to have a transition. You will have a transition from one quantum state to another quantum state, and you can measure that probability as it has to be the square of this, as the square of the expectation value of the perturbation that you have introduced in the system. So what is happening here? So two things are happening. For adiabatic approximation, so when we talk about the adiabatic approximation, what we have this Pnn tending to 0. So you will say no transitions. There are no transitions taking place for the system. Your electron is not making a transition from the ground state to the first excited state. But if you treat your problem with certain approximation, so for adiabatic approximation, Pnn is 0. For certain approximation, this Pnn is certainly calculable. So it is psi n v of t psi n, this is m, this is whole square of it. So what is happening? In this case, you have perturbation, but this perturbation is not sufficient enough for the electron in the ground state to go into the excited state. But when you go with certain approximation, it certainly does give us the probability of the transition. And if you have a system in which you apply the external perturbation to the system, the electron in the ground state will make a transition. There's a finite probability that can be measured by this equation. There's a finite probability that this electron will make a transition to another quantum state. So I hope that to some extent the students will achieve a state of idea about adiabatic approximation and certain approximations. So with this, I would like to say goodbye, and I would like to stop it here.